Hi there, Mr. Holcomb here with another episode of The Math Behind the Modules. All right, lesson 5, irrational exponents. What are 2 to the power of the square root of 2 and 2 to the pi? All right, before I start this lesson, let's review what rational and irrational mean. So in this lesson, they're talking about irrational exponents. Okay, well, what is an irrational number? So if we have this number line here centered at 0, and I start going over here, let's just do a review of all numbers sets. So if I start, let me get rid of this 0. So I start at 1 and I go to infinity. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, so on. Those are counting numbers or natural numbers. Okay, that's the set of naturals. Then I add 0. So it's no longer the set of natural numbers because 0 is not a natural number, but it is a whole number. So the whole set of whole numbers is the set of all naturals with 0 included. And we're going to build our way back up to the largest set of reals. So then if I go to -1, -2, -3, -4, now we're talking about integers. So the set of integers is the set of all natural numbers and the set of all whole numbers. And this goes to infinity, of course. So these are natural, whole, and now I have the set of integers going from left to right, all numbers positive, negative, no decimals or fractions. But then when I start putting in, let's say 1/2 or 1.1, all these decimals and fractions in between, now we're talking about rational numbers. So now we're talking about the set of all rational numbers. Okay, and the root word for rational is ratio, which means they can be represented in the form of P divided by Q, where Q does not equal 0 because I can't divide by 0. So rational numbers are now all of these. So let's recap. Rational numbers are therefore all naturals, all whole, all integers, plus fractions that are in between these. So now we're going to get to the term irrational. What is irrational? Well, there's a real famous number that's right about here, a little bit more than 3, 3.14159, and on and on and on forever and ever, non-repeating, non-terminating decimal. That's pi. Pi is irrational. Well, what else is irrational? Well, the square root of 1 is 1. The square root of 2 is square root of 2. What's the square root of 2? 1.4142, and guess what? That's going to keep going. 1.4142. That should not be a dot there. And go on forever and ever and ever, non-repeating, non-terminating decimal. The square root of 3, same thing. The square root of 4 is 2. The square root of 5, the square root of 6, the square root of 7, the square root of 8, the square root of 9 is 3. So what I'm pointing out here is perfect squares are natural numbers. They're whole numbers. They're integers. Okay? Non-perfect squares, everything in between the perfect squares, are irrational numbers. And I could also say the cubed root of 1 is 1. The cubed root of 2 is irrational. The cubed root of 3, the cubed root of 4, the cubed root of 5, 6, 7, 8, the cubed root of 9, or 8, I'm sorry, the cube root of 8 is 2. 2 times 2 is 4 times 2 is 8. So the cubed root of 8 is 2. So it works for any number of roots as long as it cannot be a an integer when simplifying, it is irrational. So there's a quick lesson on the number sets in the set of reals. Now let's get into the lesson. Exercise 1. Write the following finite decimals as fractions. You do not need to reduce to lowest terms. Okay, so let me get my pen ready here. 1. Well, 1 equals 1 divided by 1. 2 divided by 2. Anything divided by itself is 1. 1.4 equals. Now, the easiest way to do a fraction, write the following finite decimals as fractions. So 1.4, instead of saying 1.4, why don't we just say 1 4 tenths, right? If you just say it that way, 1 4 tenths is 1 over 1 4 tenths, and 10 times 1 is 10 plus 4 is 14 over 10. So there is 1.4 as a fraction. Next one is 1.41. Let me change colors in between these because it's going to get a little close. 1.41 is 1 and 41 100ths. 100 times 1 is 100 plus 41 is 141 over 100. 1.414 is 1 and 414 1,000ths, 10th, 100th, 1000th. And that is going to simplify to 1,000 times 1 plus 414 is 1,414 divided by 1,000. All right, continuing on, 1.4142. 1.4142 equals 1 and 4,142 tenth, 100th, 1000th, 10,000. 10,000 times 1 plus 4,142 is 14,142 over 10,000. Okay, and then finally 1.4141 is 1 and 41,421 over 10th, 100th, 1000th, 10,000th, 100,000. 100,000 times 1 is 100,000 plus 414,000. Or I'm sorry, 41,421 is 141,421 100,000ths. And there we go. Okay, so now part B says to write 2 to the 1.4, 2 to the 1.41, 2 to the 1.414, and 2 to the 1.4142 in radical form of the form of the nth root of 2 to the m. Okay, last lesson at the end, I should have probably done this, but I cheated and I used my calculator, and just to save time in the lesson, but now I'm addressing it. So here we go. So if you watched lesson 4, you know what I mean, from start to finish. Anyway, 2.14 can be rewritten as 2 to the 1.4 can be rewritten now as 2, and that is 14. Remember, 1.4 is 1 and 4 tenths, which is 10 plus 4, 14 tenths. Okay, so that you just think of it as going over, if this is over here, that's 14 tenths. So 2 to the 14 over 10. And then once I do that, I have my m and my n. So that is going to be the same as the root with 2 inside. The denominator is my index, the numerator is my power. Okay, and that's how you do it. Next one, 2 to the 1.41 is 2 to the 141 over 100. And to write that, I would just write my radical with my 2 as my radicand. The denominator is my index. The power is my numerator. So it's 100th root of 2 to the 141. And then 2 to the 1.414, 10th, 100th, 1000th, that would equal 1,414, 2 to the 1,414 hundredths, or I mean thousandths. That's 1,414 1,000ths, 1 and 414 hundredths, tenths, hundredths, thousandths, 1 and 414 thousandths. Well, 1 is 1,000 thousandths, so it's 1,414 thousandths. That's going to be the 1,000th root of 2 to the 1,414. And finally, 2 to the 1.4142 equals 2 to that number without the decimal, 10th, 100th, 1000th, 10,000th. Okay, and that's an exponent, by the way. It's not 2 and. So let me move this 2 down if I can. I can't. Now I can. Let's put that as a power. Okay, and that is going to equal the 10,000th root of 2 to the 1,414. All right, now part C says to use a calculator to compute decimal approximations of the radical expressions you found in part B to 5 decimal places. For each approximation, underline the digits that are also in the previous approximation, starting with 2.00000 done for you below. What do you notice? So 2 to the 1 equals 2, which equals 2.00000. Okay. So the next thing we're going to do, I'll just do it color coded like I did up here. And I'm going to say 2 to the 1.4 equals. So it says of the radical expressions. So I'm going to do the 10th root of 2 to the 14. So to do a 10th root, you put 10, and then you press math, and then you hit X root. So that's the 5. So now I have the 10th root of 2 to the power of 14. So that's how you enter that in your calculator. And you hit enter. And I got 2.63901, 2.63901. It says use a calculator to compute decimal approximations of radical expressions found part B to, now I'm going to highlight this, to 5 decimal places. So if I go 1, 2, 3, 4, 5, the 5th decimal place is a 1. In order to round, you have to go 1 more, 6, and if it's 5 or more, you round this one up, or if it's 4 or less, you truncate or leave it that. So that 1 needs to get changed because 5 is greater than, or 5 would round it up to 2. Okay, so that's the first one, rounded to 5 decimal places. So it says for each approximation, underline the digits that are also in the previous approximation, starting with this here. So this number was here, but nothing else was. 0 is now a 6. That's all I underline. That's what they mean there. Now I'm going to do 2 to the 1.41, which equals, and I'm going to put the radical in my calculator, 100, math, 5 for X root. So there's the 100th root of 2 to the power of 141. and I hit enter, and I get 2.657.3. And then the 7, I look at the next one, it's a 1, so that's going to truncate to 7. And it says to underline what we had in the prior. So now 2.6 matches 2.6, but the 3 now became a 5. All right, and now we do 2 to the 1.414 equals, and that is 1,000th root of, so I'm going to put 1,000 math 5 2 to the power of 1,414. Enter. What did I do wrong? One-thousandth root of 2 to the 1,414. Enter. Oh, error, overflow. So the calculator can't even do this. Interesting. All right, let me try something else. Let me do 2 to the 1.414, see what happens. Okay, so I cannot put it in radical form, the calculator, the TI cannot handle it in radical form, so I have to put in the decimal form. And that came out to be 2.6647. Okay, 1, 2, 3, 4. The 5th one's a 4, the 6th one's a 9, that would round to 5. 2, 6 is still the only thing that repeats. 3 became 5, 5 became 6. So I'm still only underlining 2 there. And then finally, we're going to do 2 to the 1.414. And I'm going to try to enter this again. I'm really surprised it can't handle it in radical form, but it can handle it in exponential form. So I'm going to try it just one more time, just for kicks. So it's 10,000 math 5. So the 10,000th root of 2 to the power of 14142. 14142. Enter. Error overflow. Okay, so if I clear that and put 2 to the power of 1.4142, it calculates it. Interesting. So that comes out to be 2.6651. There's 4 decimal places. The 5th decimal place is a 1, but this 9 will round it up to 2. And now you can see we have a repeat of this 266. Okay. So underlying the digits that are also in the previous approximation, starting with 2, what do you notice? Well, it's starting to repeat the prior, and it's going to get more and more of the digits are becoming the same. All right, page 2 brings us to exercise 2, but before I continue on, the teacher's edition says students cannot find 2 to the power of 1414 on most calculators because it is 426 digits long. So it says error overflow. Okay. So if I try to do like I did, 1,000 math 5 2 to the power of 1414, I get that same error overflow. Okay. So what the book suggests you enter it as is you use parentheses and you do the 1,000 math 5, 2, and then you close the parentheses, and then you take it to the power of 14, 14, and the calculator can then do the calculation because it's doing order of operations. It's taking the 10th or the 1000th root of 2, which is a really, really small number, and taking that to the power of 1414. So when it does it in that order, it gives you an answer. Okay, so it doesn't overflow before having to come back to a smaller number. It gets smaller first, then bigger, and the calculator can handle that. So that's just something, a way of entering that little trick. Okay, now exercise 2 on page 2 says, write 6 terms of a sequence that a calculator can use to approximate 2 to the power of pi. Okay, so before I do that, I want to go back to part C in page 1. And looking at this, we're getting a number 2.66512. So what number is that actually becoming? Notice the name of the lesson. So if I took 2 to the power of the square root of 2, what do I get? I get 2.66514. This is 2.66512. And the further out I go, the more accurate I'm getting. So what we're really doing here is approximating an irrational exponent, just so that you're aware. Okay, so now we're going to do that using the exponent of pi. Okay, so I brought a graph in of, this is the function f of x equals 2 to the x. So when x is 0, 2 to the 0 is 1, that'd be right here. When x is 1, 2 to the 1 is 2. When x is 2, 2 squared is 4. And when x is 3, 2 times 2 times 2 is 8. Okay, so those are those points right there. So what we're really saying is, what is f of pi? Well, pi is the approximation 3.14159. So pi is somewhere in this vicinity here. And the square root, what is f of, actually I should change this to red. Okay. And then let me change to a different color here. Let me erase this f of here and change to blue. And f of the square root of 2, which we've already done on the previous page. Well, what is the square root of 2? The square root of 2 is 2.66514 something. We're getting closer and closer. So 2.665. So it is 2.6, which is a little bit more than 2.5. It's somewhere over here. So somewhere in this vicinity is 2 to the power of the square root of 2. And it's 5 point something. 2 to the power of pi, which is 3.14159, is 8 point something. So this graph is a continuous function. It does not skip over these irrational values that we can substitute into this function. And I'm just trying to explain to you that that's what we're trying to do, is find a decimal approximation of these irrational values. Okay, so in exercise 2, it asks us to write 6 terms of a sequence that a calculator can use to approximate 2 to the power of pi. And it says, hint, pi is approximately or equal to 3.14159 ... meaning it continues forever and ever. So 6 terms of a sequence. So the first one would be 2 to the 3rd. Okay, rounding that to a whole number. Okay, but we want to get more accurate than 2 cubed. So I know that 2 cubed is 8. So if I go to 3.1, 2 to the 3.1 is more accurate than 2 to the 3. That is going to give us 8 point something. And I'll put that in my calculator just for kicks as we're doing this. 2 to the power of 3 is 8. 2 to the power of 3.1 is 8.57. So now we're already above 8.5. And then the next number we're going to put in is 2 to the 3.14. And when I do that, 2 to the power of 3.14, let me just show these at the same time, is 8.8. So now it's higher than 8.5, it's 8.8. Okay, so it's getting more accurate. And then we're going to do 2 to the 3.141. So 2 to the 3.141 is 8.8. Now this one became a 2. We're getting more accurate. And then finally, actually we got a couple more to do. 2 to the 3.1415 is 3.1415 is 8.82. Now this one got greater. Now we're out to 4 1,000ths instead of 1 1,000th. And finally, the sixth one would be 2 to the 3.14159. So I'm just going to do second entry and add the 9. I guess that's easier than typing it all in. And that 4 in the fourth place became a 9. Okay. So write 6 terms of a sequence. So this would be a sequence, a set of values that are going to continue to infinity, and then close the set. So there is part A. All right, part B, compute 2 to the 3.14 and 2 to the pi on your calculator. So 2 to the power of 3.14, enter, and 2 to the power of second, pi's right here. It's the blue command, so you hit second and this caret symbol. We'll put pi there and hit enter. Okay, so I'd say 2 to the 3.14 equals 8.8152400927. And since I said equals, I'll just show that it continues forever. All right, and then I'm going to do 2 to the pi equals 8.8249777827 ... And it says, in which digit do they start to differ? So here's an 8, here's an 8, 8.8, 8.8, 8.81, 8.82. In which digit? It is the 100th. Okay. C says, how could you improve the accuracy of your estimate of 2 to the pi? Okay, so the answer to that is include more digits of the decimal approximation of pi in the exponent. Okay, so hopefully that is understandable. So that's pretty much it for this page. Okay, page 3 brings us to the end of a really short lesson 5. Go to your problem set.